All right, hello. Welcome to my project. This is project presentation 4 for my Math Calculus 3 class, Stumbling Down a Hill. All right, so basically we've been going over the concepts of trying to figure out where basins are in functions whenever we're analyzing a large multi-dimensional function. So we're going to go right ahead and talk about how it's going to be when we simulate the movement of particles through an energy landscape using the gradient descent. So the idea is something is rolling into a particle, a ball, whatever, is rolling into the bottom of a basin, basically, inside of a function. So we're going to use a couple of simple examples, and also we're going to discuss some things that we've learned. We'll use it with the stuff that we've learned in Chapter 4. All right, so first, we're going to go over example 1. So this is an elliptic paraboloid. So we're starting at the position of 2, 3 in the xy plane. So the simple thing that we do is basically we described the descent vector concept as basically subtracting taking whatever we calculated and subtracting it out. So we calculate each vector in the descent, or each different set of points for the vector, and then we subtract those vector values from the points of that we were calculating previously on the previous step. So for this function, it was to the 1/4 here. So x and y to the f of xy equals 1/4 times x squared plus y squared. So we go right ahead and we basically do a simple, the first thing we do is we find the gradient vectors of each. So, we find the f of x and f sub y, f sub x, and we find those values right here. So those are our steep descents. Basically, I guess the steepness of them is measured out in what they are as new formulas, as the derivatives, the partial derivatives of each. And then what we do is we multiply those partial derivatives by these values, and then subtract them by those values. So 1/2 times 2 is 1, 1/2 times 3 is 1.5. We subtract those both from those. We subtract those from the original points, and we get 1, 1.5 for our new points. And we kind of do this so on until eventually we're kind of getting close to 0. So eventually what happens is we get to 0. But I remember what our teacher kind of wanted us to discuss was what happens when we get to the minimum point. What's the true minimum position, right? So the minimum position is 0. So that's what we see. But how do we know it's the true minimum? So I think really what I kind of figured out, the easiest thing that I could find for understanding that this was the true minimum was kind of calculating the true minimum with some other ways. So we basically did the secondary derivatives of each of the partials. So f of x, 1/2, f of y is 1/2, f sub x comma y is 0, because you're going to have either f of 1/2 or x of 1/2, and then it's going to go to the opposite of that. So once it goes to the opposite of that, it's going to immediately go to 0, because that's not going to be in the function anymore. So it goes to 0. So we got 1/2, 1/2, and 0. And when we do the determinant, we go ahead and plug these both in. So we literally get 1/2 squared minus 0. So that becomes, after we do the f of x and the y of y using the formula for the determinant, and it's 1/4. 1/4 is greater than 0. And f of x, f of x sub x, f sub x is also greater than 0, because it is 1/2. So there was I remember reading through there was a segment that I saw online that discussed the rules of each. And when I was doing my math homework, there were, in some of the videos, they would discuss some of the rules of each, and I was able to look them up. And what I found was if Yeah, if the determinant is greater than 0 and f of x is greater than 0, then the point at AB, f of AB, is going to be at a local minimum. So this is a minimum. So we know for a fact that this is a minimum. Now, how do we know it's the complete minimum? Well, because if we try to zero it out again, and we try to go lower again using the same function that we created from before using the gradients, 0 minus 0, 0 minus 0, 0 is going to be 0, 0. Like, we're literally stuck. We're in the bottom. So in theory, according to this, we are at the true minimum. And if we graph it, it becomes the true minimum. I will not exactly show it. Well, I'll show it here. I'll kind of do a demonstration of what it's supposed to look like. So what it's supposed to look like is you kind of, I'm showing it as a kind of a three-dimensional thing. It's literally just kind of like a bowl. That's what it is. It's literally just a bowl. And 0 is literally right at the bottom of the bowl. So we already know, therefore, that this is definitely, with the graph and with this rule of the determinant and all that stuff, we know for a fact that that is the true 0 on it. And I think this totally makes sense just because of what I see with the graph and everything else and the rules of the determinant. It all makes a lot of sense to me for this problem. All right, now we're going to move on to example 2. So it's a little more complicated. It's a lot. It's a pretty interesting, function. You've got your exponent to the 0.1 times x, and then sine x and cosine x. So we kind of had to rewrite it and do all that stuff. So we did the f sub x and the f sub x and the f sub y, and we got both of those values right here. So when we did the derivatives and stuff, we found that it was e to the 0.1x, e to the negative 0.1x, which that'll always stay the same, times sine x, cosine y, all that stuff. And we got that value. So this is what we got for the f sub x. And then for the f sub y, so as you can see, because we multiplied all these all the values here, e to the negative 0.1x times sine x, and then we derive this portion, then multiply by cosine of y because we're doing the f sub x portion. So e to the 0.1x, or f to f of x equals negative 0.1 e to the negative 0.1x, because the derivative of that is just literally going to be bringing the base level of the exponent down and then keeping the x value. And then times sine of x plus e, because it's the product rule, so it's times sine of x, so that's not going to change there, plus the original e to the exponent to the 0.1x times the derivative of sine x, which is cosine x, and so we get that value. And then for the y, we keep it all here. We're doing it based off of the cosine y, so we're instead multiplying this portion with the x by the derivative of cosine y, and that becomes negative sine of x. So negative sine of x times that becomes negative e to the negative 0.1x sine x sine y, right? Now, another thing that I found when I was doing this was that doing like a one-to-one subtraction is way too steep because it immediately goes into the negative numbers, and then that kind of just makes everything really complicated. And I when I'm looking at the graph, it does not go with that. It doesn't even, like, the values don't even go into the negatives. Like, it's just going too steep. We can't really analyze it as well. So we're doing it a little different. Instead, we kind of reduce I guess I'm going to call it the slope, but the gradient slope. I know slope and gradient isn't the same thing. Well, I'll just call it the gradient. But basically, we did the gradient reduction of 0.1 on both sides. So basically what we did was we multiplied the gradient formula. Whatever we're subtracting from the points with the gradient, we multiply what it's being subtracted from by 0.1. Then that way we're going down slower, and we have a little bit more wiggle room to kind of analyze the function. So what I did then was we used that function. So f of x and f of y, we did the separate ones, did the analysis for both, plugged the values in, and these are the values that we got. And then what we did is we take the starting point. For this one, it's 1, 1. Take the starting point, subtract it from 0.1, obviously, the thing to reduce it, because if we went the whole thing, it would go down way too fast. So 0.1 times the values that we came up with, and then that gave us the new value, 0.977, comma 1.0641, so for the x and the y. And that's for x1, y1 after one movement. I'm going to call that a movement, I guess, with every gradient movement, every roll of the ball, every movement, we're kind of, measuring it out. And then we take the next one, 0.977, 1.06, it's the same value. And then what we're doing is we got the f of x and the f of y. I did it separately here. I didn't write it down. I just did it through my Desmos Scientific. I used a tip from somebody to get that done a little quicker, because it's a really long calculation. But yeah, you're doing the cosine. You're doing the e to that number, to the smaller number, to the -1, and then -0.1, and the sine and the sine, and you're getting those two different values. So what we get now is we get the same thing. The point that we have from the step before, minus 0.1, because we can't do the full 1, times the two new numbers that we've calculated, and then it goes down. X2, Y2 is this number now. And notice two things. Notice that we have two different things going on. We have these numbers for the f sub x and the f sub y. They're decreasing. They're both, so see this, this f of x on the second step is smaller than this one. And then the f of y on this step is smaller than the previous one as well. So they're getting smaller. So as you can see, we see it even more here. Once we go down to here, it's smaller than the last one. This is smaller than the last one. So they're both just decreasing in the third and final step. And then we'll let's look at 4-2, because I graphed two different points. I wanted to not graph two different points, but calculate for two different points. F of x, 4,2, and then f of y, 4,2. We got those values, plugged them in with the formulas from before for the f sub x and the f sub y as the partial derivatives. And then we take that point, subtract it from 0.1 again, because that we can't do one full measure because it'll go way too steep. And we get this value. We get 3.938 and 1.9538. And then let's take a look just at what the separate gradients are. So the gradient from the previous one, and then this is the gradient from let's do the gradient from the second step. Gradient from the second step. So notice how it's getting smaller. The gradient from the second step is decreasing in that side. And then as we go down, but also in this side, the gradient is increasing. So it's going into a different spot. That's kind of what the point is, I think, between these two. So the gradients here, and then we have the gradients for the second step. I think I moved the decimal there a little too far. So we take those new gradients and we got them down all the way down to here. So for both of them, they're both going into, and the proof that we said for how to prove that these are basically going into different, okay, so it's those two things. So I'm just kind of showing you what happens. And the goal here was to make sure that they landed in different basins, right? So let's see. So basically the thing that I noticed is that both of the gradients are decreasing. Both rates are decreasing in the slope further and further, so we are descending. And 4-2 is kind of going in a little bit like deeper, I guess, as its gradients are a little bit smaller. They're a little more shallow, so basically it's approaching a different spot in the 3D graph. So when I graphed this thing in 3D, I kind of zoomed out on it, and I noticed that the 3D graph is it has different basins, like they're all different. Like it kind of, as it goes on, the basins get deeper and deeper and shallower. So notice that the gradients are different. The gradients are different for each. So those different gradients basically are what we kind of use to figure out if we're going into, is kind of what I'm using as like the way to verify that it's going into a different part of the basin. So it's moving downward, and they're moving at different basins because they both have slightly different gradient alterations. And also the points are pretty far from each other. To confirm my theory, when I graphed it, I saw that the points were pretty far from each other, and they're far enough that they are definitely they're starting in two different basins. So we had a proof of it for graphically speaking, and we have the proof for it with the mathematics that we are doing right here as well. And then trying to make sure that I'm looking at the graph correctly to say this is right. Yeah, because I'm looking at the graph, and I can't pull the graph here because my thing is not working. But yeah. So, and then the other thing, what we were trying to prove. So those were basically my two main points. Was that the gradients were slightly different between 4.2 and 1.1, but they're both changing. They're both, going down or maybe moving a little bit differently. So you know that it's in a different spot. They're both in different spots. So they are probably more than likely going to different basins. And it looked that way on the graph as well. I kind of tried to look at where the points are, and it looks like they're both on opposite sides, kind of going to different. The ball, I guess, would be rolling into two different points from those 2 points. And then there are another thing that he wanted to bring up in the project. There are specific points on the surface that cause gradient descent to fail. So he wanted me to think about that, about what it's limited to. So I noticed this thing. This, I guess I'm going to call it an algorithm because it's basically a set of instructions. That's what an algorithm is. This algorithm is limited by the minimums and the maximums. That's what I think. Once you're right at a point of a maximum or a minimum, the method won't be able to go up or down. So it's basically going to be perceiving the point as, at that point, is stuck in place. So what's going to happen is it's going to be stuck on the top or the bottom of the slope, because then you can't subtract any further. I'm not going to try to find the exact coordinates of one of these points just because it's a lot more math, but that's kind of the general idea of it. And then we're going to go on to the third example. We're going to pick this function. This is the function that we picked here for that example. So I did the simple calculations for each of the gradients. So what we did was we found the separate so the separate gradient number, the separate gradients, so the f sub numbers, or the partials. So the partials, so we've got the x partial, the y partial, the z partial, and the w partial, because this is a 4-variable function. So that's what we found for all of our partials. I don't really think I have to explain this because we've already done partials so much in this class for the last chapter, last chapter or two, that we pretty much know the last chapter, that we kind of know what's going on. And then I evaluated for the change in f, for the function portion, the change in the function with these gradients. And what I noticed is they all go to 0. So this whole thing goes to 0. And basically what I'm seeing is that it's stuck because like it's identically 0 at the initial point. So everything is starting at 0 and it's ending at 0. And I can't go, if I'm going to 0 now and I try to plug this in again, it's just going to be 0 again. Everything, because every variable, every number and everything is attached to a variable. So if these are all 0, it's going to go to 0 again. So as you can tell, it's going to be stuck at 0, 0, 0, 0. Now, are we moving toward, like, so what are we trying to think about here? So if I did 3 iterations of the gradient descent, it's going to give me 0 again and again and again. That's what I noticed with the starting point. Like, so am I going to be confident that the algorithm is leading me toward a basin? No. And I think it's because we're basically stuck. We're not able to figure out where we're at, because every time I did it, if I do it 3 times, it's going to get me 0 again and again and again, because the number is going to be nothing now. There's going to be no numbers. So none of this is going to work. And there's no way that we can really prove where we're at. So so he asks then, what is the approximate value of the basin? Well, I mean, there's different signs and stuff that we have here, and the way it's not really a confident algorithm. We're not really leading to the bottom of a basin. We're stuck. So even with using analyses of like different things, doing just on the basis of the 3 points alone, going to 0, 0, 0, 0, we're not going anywhere. So I think what could be causing this behavior? I think really it's just the limitation of the function, not the function, the instruction set, the algorithm that the teacher is showing us here, that Peter is showing us. It doesn't get us exactly where we want to be. So every time we do the iteration, it's going to go to 0, 0, 0. And if I do anything else, it's not going to give me any valuable information for the points. So I think really what could be causing this behavior is just the limitation of the instruction set. So now we go on to the next part, which is the problem. So now what's the problem with this stuff? So the problem with this function that's brought up is that our teacher is saying that it always comes to a single position, but it prevents us from finding the answer that we want. So when we looked at that curve from before, we see that we, go somewhere and there's 2 different basins, and the function is going to stop at a specific basin depending on the side that we approach the function from, whether that be right or left. So what's going to happen is we're literally going to be limited in our, we're going to be limited by that factor. So basically he told me to come up with some ideas. So I'm going to read an idea that I had. So I said, basically, if one could analyze a dimension by stepping it down into a lower dimension as slices, one could do the same with this exact idea, right? So in my view, the function could be analyzed with a more basic function to find the lowest possible y value and correlate that with the exact x value to reach the crater or the basin. I'm thinking that we could slice the function and analyze it into smaller and more manageable like pieces or dimensions. So for example, like a 4D image can be turned into multiple 3D images, for example, because supposedly in the 4th dimension we're comprehending a constantly adjusting 3-dimensional object when we're in the 4th dimension. And then when we're in the 3rd dimension, we're seeing constantly adjusting 2-dimensional objects, because we can move in 2 different points. So let's look at it from a 3D perspective to make it a little simpler. If we did a 3D perspective, in class, when we graph something in 3D, we see that we can put it into multiple 2D angles. where we're only seeing two different variables, whether that be x or the y plane. We're only seeing like two sets of planes together. So we're able to see 2D portions of the function. So I'm saying, why don't we do something where we could get the multiple angles of whatever something is doing in said dimension, and it would give us a way to analyze it at that exact point with a bunch of estimates from all of these other points coming together. So it's just expanding the general idea of having a computer do the calculations many times like this for us, like throwing something at a wall and hoping we can catch it. So it's not super efficient, but it's literally just, I'm just kind of expanding on the idea of this, because literally we're just taking a point and we're kind of randomly just going down in the gradient and hoping that we get to where we want to be. So I tried thinking about it a little further, and I said maybe we could expand on it and have a system that recognizes like specific patterns, a computer, we could have an AI or something that's recognizing specific patterns in various functions and use those to piece together parts of a much more difficult function. And the patterns would be recognized in various slices. So we would be knowing a specific plane in the 3D or higher function will have however many possible minimums in that exact spot. So first goes for the lowest point, and the second tries to compute in a simpler subfunction with recognized patterns to know where the basins may theoretically be. So it's kind of like it's like it has a subset of functions saved that it already knows exactly where certain things are. Like, if we have like all these memorized functions already, like if we have a basic parabola, we know exactly where the end of the bottom of the parabola is supposed to be, right? And if we have other functions where we could kind of simulate that, and it could predict the patterns of those functions, and then maybe it could do it with 3D functions, and then maybe it could expand upon it with 4D functions, etc. It would constantly be learning. That's why I'm saying using an AI algorithm to constantly be learning these different patterns for each dimensional subtype of the function. And then that way we can cover all the dimensions and analyze exactly what we want to analyze at that specific point of where the ball is supposed to be in whatever dimensional space we're trying to theorize. So that's kind of the way I'm viewing it, is I'm either seeing AI or I'm seeing kind of just throwing things more at a wall, but doing it with the dimension before. So we're kind of just losing dimensions, which is kind of already what we're doing. But I'm thinking maybe doing it, I don't know how to explain it, maybe doing it almost like from more angles, more than just one angle. So instead of going like, we're going multiple dimensions down, and we're kind of seeing what things are at the 2D scale, so that way it helps us understand what's going on the 3D scale and the 4D scale and all that, going from whatever dimension we're at now when we're doing a function. So that's kind of just my general idea. I'm not going to do any calculations with this because I have no idea where to start for this, but yeah, that's my general idea with it. So that concludes my project for project number 4.